Okay, so we're going to use the principle of complete induction to establish that a to the n minus 1 is equal to a minus 1 times this sum for all n bigger than or equal to 1. And the hint that's going to be really useful to us that Burton gave was a to the n plus 1 minus 1 is equal to a plus 1 times a to the n minus 1 minus a times a to the n minus 1 minus 1. And I'm not going to derive this. This is easily verifiable. So we're going to do proof by PCI, principle of complete induction. Our base step, consider P of 1. So that's going to be a to the 1 minus 1, which is just a minus 1 on the left-hand side. And on the right-hand side, it's going to be a minus 1 times a to the 1 minus 1, because that's as far as we can go in this sum, right? Which is a minus 1. And a to the 1 minus 1 is a to the 0, so that's just 1, which is a minus 1. So it checks out. Let's look at the second one. So consider P of 2. So it's going to be a squared minus 1, which is the difference of squares, right? So this is a minus 1 times a plus 1. Notice how I put the a minus 1 in front, because that's what I clearly want, right? And then the right-hand side, it's going to be a minus 1 times, and then it's going to be a to the 2 minus 1, and then plus a to the 2 minus 2, right? And then that's going to be equal to a minus 1 times a plus 1, which is exactly what we want. Now, let's go ahead and move on to our induction step. So for the induction step, for complete induction, we're going to assume all of them are true up to the kth term, right? And then try to prove the k plus 1 term. So we're going to suppose P of 1 is true, P of 2, all the way to, let's do P of k minus 1 and P of k are all true. Okay? So, let's see. So, now let's go ahead and look at consider a to the k plus 1, because we want to show that this formula works for if we plug in k plus 1. Oh, a to the k plus 1 minus 1, right? And look, this is where our hint is going to come in, because a to the k plus 1 minus 1 is this, right? Oh. Okay, so let's use our hint. So this is, what was it? A plus 1 times a to the n minus 1. And then it's minus a times a to the n minus 1 minus 1. Okay, so now this is going to be a plus 1. Oh, of course, it's not n, right? In this case, it's a k, right? In this case, it's not n, it's k. So let's go ahead and fix that really quick. K, k. Okay, so now remember our induction step, we assumed that this formula was true for 1, 2, all the way to k minus 1 and k. And look, we have k and k minus 1, a sub k minus 1 and a sub k minus 1 minus 1. See that? So we can assume that this formula works for those two, right? So that's why Burton generously gave us that, right? So that means a sub k minus 1 is equal to a minus 1 times a sub k, it's a sub k minus 1 plus a sub k minus 2 plus dot 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 plus a plus 1. Yep. And then minus a times, and then the same thing here. It's a minus 1, and then it's going to be a sub k minus 1 plus a sub k minus 2. I'm sorry, k minus 1 minus 2 plus dot 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 plus a plus 1. Or, right, we don't really need to do this. It's just starting with k minus 2 and k minus 3, right? So let me go ahead and erase those. So k minus 1 and k minus 3. I'm sorry, k minus 2 and k minus 3. Okay, so here, this is where we have a minus 1 term in both of these. So we have a minus 1, and then we're going to be left with a plus 1 times a sub k minus 1 plus a sub k minus 2 plus dot 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 plus a plus 1. And then, we can't close that. Minus, so now we have minus a times a sub k minus 2 plus a sub k minus 3 plus dot 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 plus a plus 1. And now we close it, right? We factored out the a minus 1, which equals, so I see what's going on here. We have a minus 1 in the front, and then we have, look at this, we have a sub k, right, plus a sub k minus 1 plus a sub k minus 2 plus dot 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 plus a squared plus a, and then we're going to do plus, because 1 times a sub k minus 1, so a sub k minus 1 plus a sub k minus 2 plus dot 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 plus a squared plus a plus 1, right? And then that's those two, and then minus a times a sub k minus 2, a sub k minus 1, minus a sub k minus 2, minus dot dot dot, minus a squared minus a. Okay. So, look at this. These cancel, all the way to this and this and this and this. So what are we left with? We're left with a minus 1 times a sub k plus a sub k minus 1 plus a sub k minus 2 plus dot 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 plus a squared plus a, and then plus 1. And I believe this is the formula, right? Because we have a minus 1 times a sub k plus 1 minus 1 plus a sub k plus 1 minus 2 plus dot 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 plus, a plus 1. Yeah, so we were able, assuming, of course, we used the hint. And then from the hint, we use the assumption that the formula worked for a sub k minus 1 and a sub k minus 1 minus 1. And from using these, what was it? From using these two specifically, that's why we needed the complete induction, because we had to use two of the previous terms. We had to use the two previous terms in order to get that it's true for a to the k plus 1 minus 1, the next term in the sequence, right? So therefore, by PCI, for every n contained in the natural numbers, we can use positive integers. What did I use specifically? N bigger than or equal to 1, so natural numbers, right? So for all n in the natural numbers, we know a to the n minus 1 is equal to a minus 1 times a to the n minus 1 plus a to the n minus 2 plus dot 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 plus a plus 1. And that is our proof using the complete induction.